let me, I mean, I'll look up what I do.
Okay, yeah, so I'm showing the slides, but I don't have any particular slides planned, so I was just gonna see what people are interested in, and then I just have the slides there so that I can reference or I can use them to discuss anything. So I'll just start with seeing what you want to talk about.
One moment. I'll talk.
I did have one comment from, well, two comments from one from Tracy's discussion, which I just wanted to show briefly because we were talking a bit about direct detection of middle charge dark matter. So I just wanted to mention a paper I also worked on that just the picture is different papers have different conclusions about this. So this is relevant for direct detection as we were talking about. So if we have middle charge dark matter, the question is, does it get accelerated in supernova shocks? And that could be a good thing if you have a dark cosmic ray component. So the paper by Dunsky et al. Was saying maybe you can actually just use xenon experiments to look for this very energetic dark cosmic ray component. The original papers were actually claiming maybe it would get accelerated out of the disk. And I think the original paper was, the argument didn't quite make sense because they were saying if it got accelerated to above the escape velocity, then it would leave. But if it's a charged particle, then the escape velocity isn't really the relevant thing because there's magnetic fields. It'll keep diffusing in the disk. So it's a little bit more complicated. And the thing we looked at didn't completely address all these questions. But this is just to show you a plot of the millicharge versus mass. And these are all, the gray region are all the stellar constraints down here. And then there's lots of different accelerator or collider constraints up here. These are the direct detection constraints. And so if we just take all these at face value, then probably we have to live down here, which means very small charges. So I think that's one reason that the kind of signal that was asked about, the synchrotron, might be very small, unless you can live in a gap somewhere here. And then the thing we're looking at is whether it's true that this millicharge dark matter would get accelerated in a supernova. And we didn't quite answer that question because it turned out to be a lot of complicated plasma physics. But the picture of the cosmic ray acceleration itself is that there's a shock front and it's expanding very rapidly at like 1,000 kilometers per second. And so there's ambient particles here that could be millicharge dark matter or, of course, the ambient baryons. And when it goes to the shock front, it gets heated up and it can reflect back off the fields and particles here and go back across the shock front, and then that can happen again. And this process is basically Fermi acceleration, by which we have very accelerated particles. And that certainly happens for protons and electrons, but it's very unclear if that process will happen for particles with charge to mass ratio, which is much smaller than that of the proton. So this dashed line is 10 to the minus 3, the charge to mass ratio of the proton. So that process is very unclear. We couldn't really, it's hard to answer that question with a lot more plasma physics, basically. So I think that question is still very much an open question for if it's actually getting accelerated to a large extent. That being said, this dark matter, millicharge dark matter should get swept up inside this shock, and it'll probably get reprocessed by the shock a little bit through the velocity distribution. And in the end, we found that it's probably not, it's like a kind of order one effect on the velocity distribution of this dark matter particle. So these bands here are showing the minimum charge to mass ratio where this millicharge dark matter does get swept up into this supernova shock, and you have some order one effect potentially on the velocity distribution. So yeah, just a follow-up comment from that.
That's really cool.
Yes.
Thanks. Yeah. I have a question just about the intuitive understanding on the dark photon model. So my understanding is that when your dark photon is much heavier than your standard model photon, then your standard model will be milli charged under your dark E1. And then if your dark photon is lighter than your standard model photon, then the dark matter is milli charged under the standard model U1.
Yeah.
Is that the right way to think about it?
Yeah, that's what I was, trying to put as a useful way to think about it. Yeah, it's not exact, of course, because you have the small, that's like the, very different masses. We're talking about like, I guess what I'm saying is like, if the masses are like, within a factor of 10, then you'll still get a little bit of, that's not exact. You'll get a little bit of the other coupling that you didn't include, but yeah.
Right.
Exactly
So,
right.
okay. So in the case where the dark photon is heavier, the standard model does have some interaction with this dark sector of H group. Is that?
Mhm.
Okay.
Yes,
Okay,
exactly.
great.
Yeah.
Thank you.
Yeah.
That's
Can
all.
I maybe just, yeah, so like, just to clarify, I think earlier on, I was saying that, it was always this case, at least for like a heavy dark photon, that the standard model picked up the dark family charge rather than the reverse. Like, I was thinking in the context of the vacuum case, where the standard model photon is massless, like not in the
Oh,
case
yeah.
where there can be plasma masses and so on. So, yes, I agree with Tongyan, just to be clear, in case that was confusing.
Okay, well, I have another follow-up from a question that was asked. There's some discussion about whether you have to be on this freezing line. So I just found, this is actually a somewhat older paper, and there might be an updated one. I just didn't think of it in this in the break when I was making this. But from this somewhat older paper, this gives an example of this like shaded region is trying to indicate there are lots of other dark photon models where you're getting the right relic abundance, and you would see, direct detection cross sections within the reach of these proposed experiments. So this was the freeze-in line, which is you want to exactly get all your relic abundance from the freeze-in. And then this shaded region is other types of models. I think they're mainly secluded dark matter models. So meaning like you're annihilating directly to a very light dark photon, or very low mass dark photon. And that's setting the relic abundance, I believe, in this whole shaded region. So it's not the case, that you only have a model there.
Any question on this before doing the lectures, or does that mean you have more to say about like direct materials or nanomaterials for direct detection, like what makes them special or how do they work?
Yeah, so thank you for the question about, so this is about direct materials or other types of materials. So this plot I didn't have much time to go into, so I'll go back to this plot a bit. So the left plot is for this massless mediator. We have these different semiconductor experiments. So here's again silicon and germanium up here. This is diamond, another proposed experiment, just as an example of something with a somewhat higher gap. So this is like threshold of 5 EV, and these were about 1 EV threshold. And then there's been a search for materials that could have much lower thresholds. So the main examples that have been discussed so far are aluminum superconductors or superconductor targets in general, which are these purple lines here. And then direct materials, an example of which is this blue line here. So this one is the direct materials, a direct material. And the gap for a superconducting material can be as low as a few millieV or even smaller. So if you just have a metal, then you can think of it as it's a free electron gas, and you're just filling up to some Fermi energy, and you can excite above that Fermi energy easily. No problem, just give a little bit of kinetic energy. So what happens when you have a superconductor is there's this Cooper pairing, and there's a gap that develops right at the Fermi surface. So there's a very small gap. And that's actually good because it means there's a chance of actually detecting the excitations you create. They're much more long-lived in a superconductor than in a metal. So if you were to draw kind of a very loose band structure plot, this would be like a metal. Oops. So this is the Fermi energy, and this is just like a free electron dispersion. And when you get to a superconductor, you still have these states, and then there's a kind of a gap. I don't know how to draw this, but there's a kind of gap here, and then it sort of continues, and this gap is usually milli-eV. And yeah, so in principle, you could go as low as the gap. That was the original proposal. This I'm showing here just 10 milli-eV or 100 milli-eV as like thresholds you could reach along the stage to maybe getting as low as the gap. So one problem with one initial problem, it was thought that there was an initial problem with superconducting detectors. And the problem was that there's a lot of screening in a metal. So I didn't have much time to talk about this, but one way to think about the scattering in a solid state material is before we had this kind of matrix element, which was a final state e to the I q dot r, and some initial state for the hydrogen atom. So I introduced this form factor for the hydrogen atom. And it's similar for a semiconductor, but there's an important difference, which is you have to include a dielectric screening in the material. So this is a dielectric function depending on the momentum transfer and the energy. And in a metal, it's very reflective, so it means that it's very, there's a high amount of screening. And so this factor appears to be, is very large, especially at low Q, meaning short, long distances. So there's a lot of screening, and it was originally thought that actually the screening effect completely makes superconductors not very useful for dark photons, because what we're looking at is, we're looking at, like, for instance, a millicharged dark matter coming in. It creates a small field, but it's so heavily screened it doesn't do anything really. But that got corrected somewhat. So the screening effect was actually overestimated in the initial results. And so actually just this year, a bunch of people have been working on this, including us. And the corrected result looks a little bit better. So that's this line here. So screening is not quite as big as was thought. And you do get, it is worthwhile looking at these superconducting detectors. But in the meantime, there was motivation to look at other types of low gap materials because it was thought superconductors are not, they have too much screening. And that led to work on direct materials, which is good now because now we also have this other type of target material we could think about. And one of the motivations for looking at this direct material was that it had a lot less screening. And the reason was that you could think of the large amount of screening as there being a really large density of states near where the gap is. So there's a really large density of states. And the direct material, if you were to look at the band structure, it looks different. It actually has like a linear. So this is the Fermi energy, and it has a linear dispersion. So the density of states is lower, and that results in lower screening. So that was the motivation. The actual material, it's not purely linear. There will be a small gap, so it'll look something like this. So these will be like the occupied states, and then you can excite to these available states up there. So yeah, that was the motivation for looking at these. These are not as experimentally not as well understood, I think. For instance, it's clear we can get a crystal of a superconductor of some reasonable mass for direct detection, but it's not as clear that that works for Dirac material. And I think I don't know that this is not as well developed experimentally, but for the superconductor, the plan would be at some point in the future, it could you could use it as a absorber in a super CDMS like experiment, similar to what Jody was talking about.
Could you repeat what your diagram is, please?
Yeah, this is trying to show this is a band structure, which I also didn't have much time to talk about, but it's trying to show the available, so these diagrams are basically in some sort of momentum, and it's not always the true momentum, or it's not the true momentum, it's like a crystal momentum, which is another thing I didn't get time to talk about. So it's a crystal momentum versus energy. And so the band is telling you where you have available states. So you have available states like this for a direct material. And so all the states below the Fermi energy get occupied, and all the ones above are the ones you can excite to. So you could have, so basically the screening effect you can think of as is asking like, how easy is it to excite from or the screening effect is basically virtual oscillations of the occupied to unoccupied states. And that's why, that's why the band structure determines screening effects.
One or two questions on this massive mediator on the right here. So this freeze out line, isn't this, what is the massive mediator for this freeze out target line?
Yeah, for these lines, it's usually assumed just by convention in the field. Yeah, that there's 3 times. Yeah.
So it always kind of bothered me, because I mean, as you approach the resonance, can't you just move that scalar freeze out line way down? If I say, as I approach MV equals 2m chi.
Yeah, for if you're looking at, for instance, like forbidden or the resonant case, then it these do change quite a lot. I guess that I don't know if where those lines are. I don't have an example of those lines off the top of my head. They're probably in one of Josh's papers. The motivation for this was that if you take MV to be like 10 times MX or something, if you go in the other direction where it just scales as MV to some power, then it just makes it harder. It just makes it either more excluded or harder to detect. And so this is kind of an optimistic scenario where you aren't too close to any resonances and don't have to worry about that. But yeah, I agree. There's again, you can be anywhere outside of those lines, and presumably you can be outside of those lines by being near a resonance, like you're saying.
And for this asymmetric line, I have not too much experience with asymmetric dark matter other than what we've talked about here. Don't we have to say, like, specify some level of how asymmetric it is with its partner?
Oh yeah, the asymmetric line is a lower bound. So there should be an arrow here. I didn't draw. So yeah, there's a minimum amount of annihilation, and then the more annihilation there is, then the less asymmetric component is left behind.
Okay.
So that's a lower bound.
And I guess the other question I had on this plot was if there's some resonance around 300 MeV or something. In the target?
Yeah. Perception. I don't remember off the top of my head. If anyone else remembers what this feature here is.
Yeah, I can't even think what would.
Yeah. Yeah, might be related to pions. Yeah.
For us, it's for a scalar medium, is that right?
This is all for a dark photon
Oh, for
mediator.
dark photon.
Yeah.
Um, Could it be like, could it be mixing with like a rho or a phi or something? I've seen that before. I don't know if that's what this is here, because the rho is like 700 energy.
Right, because yeah, to get the annihilation into the into hadrons, yeah, you have to I think it's I don't remember exactly who did this calculation, how they obtained it, but to get the annihilation into hadrons, you should match onto various QCD resonances just from collider data. So if they might have done that, and that might be where it's from, but
Not a good, just curious.
Okay. Could you say a little bit, I think maybe you mentioned this a tiny bit, but if you have spin dependent interactions, what that would mean for condensed matter systems and how we are looking for whether that changes anything about the searches?
yeah, for spin dependent interactions, there's been not as much study on that, but one interesting study is that you could look for spin waves. So magnons are electron spin waves, basically. So they're the electron spins are kind of ordered in a particular way, and you can excite these like collective excitations of magnons. That's mainly for sub-MeV dark matter. The model space is not so clear. So again, there's not like very clear benchmarks like the kind we're seeing here. But yeah, there's been some study of exciting these spin waves. For heavier dark matter, you can just do electron scattering in the same way, because it's a good approximation that the spin states are all degenerate for what we're looking at here. So you could do that for heavier dark matter. Yeah, there just hasn't been as much study.
So is the idea with the spin waves that like a dark matter particle comes in and affects the spin of some particle in the material, and then there's sort of like a cascading effect?
So it's a little different in that it's more similar to the phonon excitations I was talking about. So just to sketch something. So for the phonon excitations, for instance, I have a lattice of nuclei, and then when the dark matter comes in, it's exciting like a collective excitation, meaning these phonons are all kind of moving together. And so for the spin dependent interactions, instead of displacements of the atoms, you're coupling to the spin wave, meaning kind of the spin is being rotated as a function of the atom position, of the ion position. So it's not that you're so again, in this regime, you're not coupling to like a single atom and then causing an effect. It's actually kind of like you're coupling to all of these atoms together.
Oh, interesting. Okay.
And causing this excitation.
Okay.
Yeah, because for very low mass dark matter, think about like the momentum transfer. This momentum transfer could be many times. It could be 1 over, say, 10 times the lattice spacing or something. So effectively, you can think of like a potential, which is like very long wavelength compared to the spacing.
Thank you.
When thinking about these spin-dependent interactions a little bit more, I know there's some, I guess there's some exotic nuclei that have some high spins or something, like you get 5-half spin nuclei or something. Is this something people think about to probe some unique models to get some of these weird nuclei with maybe even higher spins? I don't know. Maybe it's a weird question.
Yeah, you could if you want to couple to the nucleus spin, then you have to polarize this material also, and that hasn't really been studied, and in principle it should be possible. but for the spin wave case, yeah, then what you're looking for is a particularly strong magnon coupling effectively. So you look for some exotic material with effectively like high spin.
And so if you want to polarize the material, that's just experimentally difficult or for the nucleus?
I think so. Maybe an experimentalist should say, but right. If you want to polarize it, you probably want to apply some magnetic field, and then that might interfere with the actual way that you're detecting say if you're detecting by the heat deposition with the TES, that might influence your ability to detect it.
What determines if you have a phonon excitation versus like a plasmon excitation? Is it like a mass or momentum transfer?
Yeah, so for the plasmon excitation, that's coupling to electrons mainly, and it's much higher energy. So what I showed was here. So at least for a typical plasmon, the energy is much higher. It's like 16 eV. And this is, as I was saying, like a collective excitation of the electrons. So it's mainly coming from dark matter electron excitations. Whereas for the phonons, that's the collective excitation of the nuclei, and that turns out to be much lower energy. So it's 2 orders of magnitude lower, at least, in energy. So it's more like, it's going to be closer to 20 milli eV or 20 to 200 milli eV, as opposed to 20 eV. And so those could come from dark matter coupling to electrons also, because the phonons, they're collective excitations of ions. So one way we're thinking about these crystals is that we have a lattice of atoms, and there's the very loosely bound outer shell electrons, which are the valence electrons. Those are the ones that can get excited when we're looking at electron excitations. But then there's also the very tightly bound inner shell electrons. So when you talk about phonons, it's really like the nucleus plus the very, the inner shell electrons that are moving in some sense. That's one way to think about it. So you could also couple basically coherently to all the inner shell electrons, and you could also move that, or you could also create phonon excitations. But you can also create the phonon excitations by coupling to the nucleus itself. So when we're talking about dark matter nucleus interactions, that's why phonons come up a lot more, because it's the primary way to look for that. Yeah, and I can say a little bit more about phonons because I didn't really get into that. So yeah, this is just a typical toy model I like to show of phonons. So of course we have 3D lattices, but just as a toy model, you can have a 1D lattice of atoms and just kind of picture them as being connected by, effective springs with like effective spring constants. And so you can excite waves in this chain. And in this first cartoon, if you just have one type of atom and they just have this spacing A, then if you look at the normal modes of this 1D chain, then you'll get these acoustic phonons. So they have a linear dispersion. Here, at least at long wavelengths, they have a linear dispersion for reasons we talked about last time. And they'll saturate at some energy for maximum momentum, which is pi over A. And then if you have multiple types of atoms in your crystal, so here I've just drawn 2 types of atoms in your crystal, so they're distinguishable either due to different masses or they're just kind of inequivalent positions in a crystal. Then you get other types of excitations, which are these optical modes. So for instance, you could displace them out of phase, and that would be an orthogonal normal mode to the acoustic phonons. That would give you this optical branch. So this looks much more like, like localized oscillation. So that's why these end up having a finite energy even at zero momentum here. So that's roughly the picture for this optical and acoustic phonons that I was showing yesterday in this kind of plot for the response.
There's no ammo.
So yesterday, I was asking you about differentiating between what we call condensed matter systems versus molecular systems. I think that was yeah. And you mentioned when you think about molecular systems, I think you said you're thinking of like order 10 molecules or something.
You could have systems with, order 10 atoms in a molecule. And there's some papers looking at that you can actually write down the kind of full solution for energy eigenstates, or at least a very good approximation for the energy eigenstates, and that by solving some like complicated 10 atom sort of equation. Yeah. But you can't do that when you have a lattice of like 10 to the 23 atoms. Yeah.
Right. And in terms of experiments, we're never thinking about doing anything on that small scale. Where are we?
There is an experimental proposal, and actually some realization. So the idea is there are these scintillators, and they're called like organic scintillators. So this is work by Yoni Khan and a bunch of collaborators. So the picture is that there's kind of individual molecules that are crystallized in a condensed matter system. So it is kind of an intermediary. So it's not like a gas of molecules, which would be somewhat low density, like if that was your concern. So yeah, you wouldn't want to look at like individual molecules being excited. That's very low in mass, but they do have these systems where it is a condensed matter target, but it's a good approximation to think of it as individual molecules in this liquid. And so it's sort of similar to when we were talking about liquid xenon and looking at atomic ionization in liquid xenon. You're in a liquid, so it's not truly like a gas of xenon atoms, but it's not a bad approximation to just treat it as individual atoms. So they looked at this particular couple of materials, one of them called T-stilbene. I don't know why, but anyway, it's called T-stilbene, and it's a kind of molecule that has roughly around 10 atoms, so a bunch of carbon and hydrogen chains, and they looked at that as a target, and it's a scintillator, and it's actually relatively feasible to use as a kilogram scale target as well.
Just got there.
Yeah.
What's your opinion on the direction these sub-GeV dark matter searches are going to go, should go? Where's the interesting parameter space looking into the future?
So yeah, that's a interesting question. So this is my personal opinion, of course, but in terms of parameter space, I think there's definitely going to be a lot of activity in the MEV to GeV range, and that is the most interesting to me right now. With sub-MEV, there's more room to do a lot of interesting condensed matter stuff. And I'm speaking as someone who's worked quite a bit on that. I've worked quite a bit on phonon excitations. The only issue is that the model space for sub-MEV dark matter is a lot more limited. So there is this possibility for freeze-in below sub-MEV. So we go back to this plot. One of the main models being used to motivate sub-MeV is freeze-in. And that's something I work on, I'm interested in. But one open question I'd say about freeze-in is something I haven't talked much about yet, but if dark matter is millicharged, then as we saw in this discussion of the supernova constraints, there are potential plasma effects. So one is that the dark matter itself could be accelerated in supernova itself. So we see that in like, here's the MEV scale, and this actually extends even a little bit further, but definitely down here when you're in the sub-MEV region, that's where you can have these important, you can be accelerating supernova. So that's one question, what's happening there. Another question is whether the dark matter itself is going to be a plasma with plasma instabilities. So here we're talking about the dark matter interacting with this supernova shock. So with the protons, the ionized plasma there. But you can also just imagine, we have a picture of galaxy formation, which works for CDM, which is I have some galaxy and we'll have some subhalo come in and it'll merge and will form larger galaxies, so on. And if we think about what's happening here, it's like two blobs of charged particles merging if it were have millicharged dark matter. And there could be plasma instabilities forming when you have two plasmas coming in at high relative velocity. That's the idea behind cosmic ray acceleration, and it could also happen here. There's an interesting paper, kind of the first paper to really just try, well, one of the first papers to look at this in the context of freeze-in. There's a paper by Robert Lazenby exploring this, and it's really hard to get a definitive answer similar to the supernova case, but it suggests that, again, for the sub-MeV range, we have potentially, we have big impacts on structure formation from the fact that if dark matter is millicharged and you really have this plasma, and now you're talking about merging plasmas instead. So that's kind of a big question I have for these sub-MeV models, despite the fact I do think they're very interesting and motivated, but there's also a lot of questions. So that's the case for the dark photons. And then for the scalar meteors, I've looked at the parameter space, and that's also quite limited. So on the one hand, there's a lot of room for kind of looking at interesting condensed matter effects for sub-MeV, but the actual parameter space of allowed viable models, there's still a lot of questions, I'd say, here in the sub-MeV range. But for MEV to GV, yeah, there's a lot of promising stuff happening, and we'll definitely hit a lot of these benchmarks some point soon.
Thank you.
I think this was already asked, but I'm very interested. Like, do you think there would be sensitivity to solar neutrinos with this sort of detectors?
Yeah, definitely. But after we get to kilogram scale experiments. So
okay, then even more speculative, since the threshold are extremely low, less than Catherine, there might be the possibility to constrain clumps of relic neutrinos.
if the clump is very large.
Yeah, I know where it is,
Yeah.
but I mean, my question is needs to be competitive with current constraints and over densities of neutrinos.
I don't know the current constraint if you know it off the top of your head. So
I think it's 10 to the 10 of what you should expect.
okay, yeah, it could be. I'm not sure. So so keeping in mind that these are future experiments that don't exist. So these are not constraints yet, but yeah, I think at some point, yeah, I've definitely looked at what the scattering rate is. And of course it's very low because you're looking at very low energy. So you're suppressed by G Fermi times energy squared or to some power. So yeah, the cross section that you would be sensitive to is extremely small, but yeah, if it's 10 to the 10, maybe, I don't know.
But even with these low exposures, like you could, for example, be sensitive to magnetic moment of something because it's an answer to low energy. So you don't really need that much exposure. I think it's very promising.
That's true, yeah. At some point, some people were doing a study. I talked to them about this, and I don't know if they never wrote it up because it's not sensitive or they just didn't finish. But yeah, certainly, I agree with that. So if you're taking this kind of low threshold, some of these experiments, and you look at you're talking about like solar neutrinos scattering through a magnetic moment, or was that? I assumed that's what you were talking about.
Yeah.
That. Oh, okay. Yeah, you could, I think there could be some sensitivity, but I don't know the number. That study, as far as I know, never came out.
So there are no projections.
Yeah, I don't know of any projections. Yeah.
Yeah, if I may, someone else has a question. No, I'm missing something here, but I'm wondering just because I have them, these superconducting, say, RF cavities, I mean, they have a really thin layer. So it's a small, yeah, I mean, it's not a relevant exposure in terms of mass, but they can sort of bring themselves up. I mean, these are the things that I used in axion searches, for example. Can't they also be sensitive in some way? I mean, probably by a modulation signature or something, also these kinds of documents.
Can you describe the geometry a bit more?
I think they're like the X size, but can make them much bigger, but that's what we can quote is either an HTS layer on top or niobium titanium is very thin when you put them in a cryostat and a magnetic field, and this is one of these typical axion searches.
So it's a thin film.
It's a thin film, yes, but at 2 Kelvin or something, which is probably too warm.
No, yeah, that's okay. Yeah, that's okay.
So, and then you have rather high quality factors, like 100,000 and so on. So it's a very thin. I'm just wondering if there's some sort of signatures that, I mean, what you then do for the axion is sort of, I mean, you have the resonance, I mean, the shape of the resonance, which is typically much wider than the axion line itself. So you have this bump, or you have, I don't know, a bin that goes on top. And then eventually you move those and you scan. And I'm probably, I mean, people must have thought about just using those things also for other, I mean, you can do the axion, you can do the dark photon, but how about these, yes, direct, the dark matter that scatters with the electron in the superconductor that makes it, I mean, what you're saying is we want to make use of small band gap almost non-existing.
Yeah, so I'm still not sure I got the geometry correct, but if it's just, so if, for instance, if it's a thin film
Yes.
superconductor, there was some work to use, for instance, there was a group including Yonit, who will be here, Yonit Hochberg, who will be here, and they looked at superconducting nanowires. So I just mentioned that because the idea they were using is a small amount of should be a similar mass, I imagine, as what you're talking about. So it's a nanowire, just slightly different geometry, but the idea they were trying to use was also, let's use an existing device that they have and try to put some limits. For the mass they had, they did set some limits. They're currently many orders of magnitude weaker than this, I believe, but maybe they have some projections for the future. So probably the limiting thing is the mass, but we can see. Yeah.
Okay, I'll try to look up.
I don't know too much about Suzy, but are there any Suzy particles that are potential sub-GeV dark matter candidates?
I don't know of any with this direct detection signal.
Right.
So they exist with very little, with very tiny direct detection signals, but.
Just because they wouldn't interact with the materials?
Right, because I can think of, say, gravitino or something, which would, the interaction strength would just be very, very small.
You can also have a neutrino, but they don't make the really command. So it would be
Since maybe we have time, could you describe a little bit more about why the gravitino doesn't work with these direct detection skills?
Oh, just for the gravitino, then all the interactions would be like G Newton, would have a G
Oh, okay.
Newton. So,
Sure. Got it.
yeah.
That makes sense. Thank you.
Maybe we're all ready for the hike.
Yeah, we can. Yeah, of course we can still.
Can I do just like,
Sure.
in like 1 minute, a couple of follow-ups on my earlier session, since you talked about some follow-ups from the earlier session. I just wanted to know in response to some questions from earlier. So the questions about explaining the 2.5 kV line with like annihilating like dark matter. There was a paper from 2014 by Simon Beck and Pico and Lionel Park, where they looked at some annihilating dark matter models, and indeed getting the relic density and the 3.5 kV line is hard. They did a model where they worked out a model where you can do it, but it requires injecting like thousands of extra degrees of freedom into the early universe in order to get the dark matter to get the relevant. So that's one example. And the other, there was a question about, could you simultaneously try to get xenon 1 ton and the 3.5 kV line with axion-like particles. So there's a paper from earlier this year by Ariane Decker, Ivo Kebun, Fabian Zimmer, Kenny Eaton, and Shinichiro Ando, called searches for sterile neutrinos and axion-like particles from the galactic pillars with Rosita. And the answer appears to be that it's very promising to test the 3.5 kV line with Rosita, but it's very hard to simultaneously explain the 3.5 kV line and the xenon excess with the same particles, basically because to get the xenon excess without being excluded by other things, you need to dial down the coupling of photons by a lot. And for the 3.5 kV line, you want a coupling of photons. So that is my quick read of the paper. So yeah, just a follow up on a couple of
Yeah, one other thing maybe I'll advertise, since I have the figures, was this directionality stuff we talked a little bit. So I'll just show 2 examples of the directional signal you can do with these solid state targets. So this one is with a Dirac material. So again, the kind of picture was like, this is the Earth axis of rotation relative to the dark matter wind. So at t equals 0, you have like a particular axis of the crystal that's pointed with that's aligned with the dark matter wind. And then half a day later, you'll get the other axis, the perpendicular axis of the crystal aligned with the dark matter wind. And so then what you'll see is this rate, the scattering rate as a function of the time of the day, of the sidereal day actually, modulate, usually with larger effects as you go to lower mass dark matter. So this directional detection stuff is mainly for sub-MeV dark matter. So far, any studies of MeV to GeV, the effects are not quite as large. So I think the biggest one I've seen is actually from scattering, from looking at the breaking of the chemical bonds. So if you have a crystal, one approach I mentioned was you can kick a nucleus out of its lattice site, and that will create a defect. And so if you kind of have a picture of a nucleus in a crystal, it could live in a very anisotropic harmonic potential. So not a 3D harmonic, I'll say, which is symmetric, but just some anisotropic one. So as the crystal's rotating, you get a highly, it's very dependent whether you can kick the atom out depends very much on the direction of the wind. So that's the main one I've seen for MEV to GeV dark matter. Oh, sorry, the molecules also have a large directional detection as well. So I guess I should amend that. So it's not true just for sub-MeV dark matter. You also, for dark matter electron scattering, sub-MeV dark matter, it's been looked at for Dirac materials. For MEV to GeV, it's been looked at for these molecules, which of course are very anisotropic, can be very anisotropic molecules. So there's a large modulation there. And then for, okay, here it is. For phonon excitations, you also get a modulation. So it depends basically on what the phonon energies are in the crystal as you rotate. And so that's where these modulations are. You even get weird effects where the phase can flip basically depending on the mass of the dark matter, you couple to different energy. You're allowed to couple to different energy phonons or excite different energy phonons. So you can get this phase reversal when the mass is low. So for sub-MeV, you get the directionality from phonon excitations, and for MEV and above, you can get it from the threshold for creating defects in a crystal, for instance.
Can you repeat which one was the one for the lighthouses? You said it wasn't the phone excitations, it was.
Yeah, it was for sub-MeV, it's phonon excitations. Sub-MeV and nuclear recoils, you can get this directionality from phonon excitations. For sub-MeV and electron scattering, you can get it in Dirac materials, for instance, maybe also other targets. And then for MEV to GeV, the ones I've seen so far, you can get it from scattering off of electrons and molecules or breaking bonds in crystals, for instance, or maybe also it works for molecules. I don't remember if that was looked at already.
Can you comment on the compatibility of the Shannon excess and sub-GeV model mode?
I don't, I think the best models for the, or the ones that work the best for xenon 1 ton, don't necessarily give any signal for the experiments I'm talking about. That being said, I think some of the best models that I'm aware of that work, one of them is, for instance, a KeV dark photon. So that one I think works quite well. So if you have a KeV dark photon, it's being absorbed in xenon and it creates the KeV excess in electrons. So that's a sub-GeV dark matter model. It just, the signal it gives is at the KeV scale, so it's not as relevant for the experiments I'm talking about. Yeah, I think that's probably the one that works the easiest in terms of evading all the stellar constraints. There's probably other ones that work with like inelastic splittings as well. But yeah, there was a nice paper looking at the stellar basin contribution to the dark photons or axions. So in addition to so one model is just that you have dark photon being the dark matter and it's at a mass of a few keV. Another option is that the dark photon or the axion is being produced by the sun. And there's a particular contribution, which is that the sun can produce a small amount of like non-relativistic dark photons and axions. So usually when we talk about like solar axions, we just treat the axions as massless, and then you get a they're all like relativistic. But there's a small number of non-relativistic particles that can be produced if the mass is somewhat high. That's actually pretty interesting because the non-relativistic ones actually have to stick around. They don't escape the solar system because they stay bound. So there's actually a very large component of non-relativistic solar basin, as was introduced by Ken Van Tilburg. There's a not large contribution of non-relativistic dark photons. So even if it's not the dark matter, that would be another model that that would give you the xenon 110 excess. I guess in principle that that could also be a mediator for the dark matter, but I think for that mass and coupling, it wouldn't give a very large. It wouldn't fall into the freeze in and freeze out benchmarks that I've been talking about very easily. So that would be like, I believe it's dark photon masses around a few keV and couplings of 10 to minus, kinetic mixings of like 10 to minus 10 or lower. So that's very different from the kinds of couplings we talked for either of the kind of benchmark models for direct detection for sub-GeV dark matter.
So I guess if I ignore freeze out and freeze in for a second, so these dark photons can explain the xenon excess for these, you said keV scale dark photons. So I don't know, maybe I probably missed this, but what kind of experiments can probe these scale dark photons if I'm not looking at thermal cross sections or something, or is there a range of cross sections that I can explore with these kinds of condensed matter systems?
Sorry, can you go back? Are you talking about the dark photons for the xenon 110 excess, or?
Correct.
And then what was the connection with the sub-GeV or the condensed matter experiments?
I'm wondering if, so we say there's this dark photon that can maybe explain the xenon excess, and I'm wondering if there's any experiments that can probe this same mass range.
Right, so if we're talking about keV scale dark photon, the experiments I'm talking about just they could in principle, but the primary signal would be the dark photon is absorbed. So it's very similar to the photoelectric effect. So it's absorbed by the atom, and then you it creates an electron excitation of order keV. So these experiments could in principle see such a thing, but they're not really. There's kind of two issues. One is that they're much smaller mass. So for xenon 110, we have so much mass that the coupling that you need to see that signal is very, very small. So for a kilogram scale semiconductor experiment, even if you're sensitive to that energy range, you won't see it. Basically, the coupling sensitivity is much lower with a kilogram scale experiment. So that's one issue, I think, in comparing those.
You need some giant coupling, and you've probably seen that somewhere else, I guess.
Yeah. So yeah, you can do a comparison of yeah, I've done a comparison before for dark photon, dark matter, and if you just look at independent of the xenon excess, if you just look at how well like a semiconductor experiment can do, it's not. It's difficult for it to be competitive with like existing constraints from stellar emission or things like that already. And so if you want to satisfy stellar emission and get xenon 110, then you're already below that.
I see. I'll come up with many questions later. So a bit off topic, nothing to do with direct detection, I guess, really. But thinking about the dark photon, you originally introduced it saying that we have some heavy fermion that is coupled to both U1 standard model and U1 dark. Do I have to suppose that this heavy fermion exists to get kinetic mixing?
No, that it's an independent. Or you're asking, do I need a heavy fermion in the loop to get kinetic mixing, or?
Correct. Yeah. Do I need a heavy fermion that is charged under both?
That's just no, you can just write it down. It's allowed. Yeah, just as in Lagrangian. Yeah. So that's just a kind of argument for why you might generate it. So if you had that at some high scale, then you would generate it through that loop, and then it would actually run, and you would get some, you would automatically get it. It just, you could also just write it down.
Yeah.
Yeah.
That's what that. I guess another one that came to me at one thing with the last question. So we're looking at all these small scale kilogram condensed matter systems. Why not just make a giant crystal or something?
Yeah, I think, well, first, one reason is that we just want to start somewhat smaller so you always start somewhat smaller, but there is a difference, I think, in that it's, there's, I think, just some technical challenges to getting, okay, so if you had a small crystal, of course, you can just place a whole array of them, and you can have more. So in principle, yeah, you can have more. And Sensei, some future generation of Sensei and Damic is going to combine into something called Ascura, which is going to have, I think, 10 kilograms. But yeah, I think it's generally harder with these crystalline ones. You need very high quality crystals. It's possible, but it's a lot of work. And as we see, even with like a kilogram, we're getting well below some very interesting benchmarks. And with a kilogram, we're going to hit solar neutrinos. So it's possible in the future, but I think that's one reason it's a natural scale, because of solar neutrinos, for instance, and just the feasibility of dealing with crystalline detectors. It's hard to get large masses and grow large crystals, for instance, high purity crystals.
Sure.
I can just speak for Crest in this regard, and the background and the threshold stays with the size of the crystal. So the smaller you go, the lower you can have the threshold, and also the better the background gets. But of course, then you can also just take a lot of small crystals, but then you run into the problem that, at least in Crest, we are operating and analyzing them individually, so we run into the problem of manpower.
Yeah.
Okay. So there are more questions here and no more questions on Zoom. And close the session here. And thank Tongyan very much for the lecture. Up there, and we have time for for lecture. So thank you. From my point of view. And so who is the leader for the height this afternoon? Where do we